Hello, everybody. My name's Kate Soule, and as was mentioned, I'm a director of Generative AI Research at IBM. And today, I'm going to spend a little bit of time and talk about how IBM is investing in generative AI to make it a tool for enterprises to put to work. How we are trying to make generative AI move beyond something that you can experiment with to something that you can trust and put into production. So, to get started, I sit at the MIT IBM Watson AI Lab, which is a part of IBM Research up in Cambridge, Massachusetts. If you're not familiar, IBM Research is a global organization. We've been around for almost 75 years. We employ over 3,000 different research scientists across topics like AI, quantum computing, and other advanced technologies. And we have over 12 different Nobel Prizes and Turing Awards that we've won throughout our time. And it's this team that is building IBM's generative AI models for our products, like our Watson X series. When I think about generative AI, I think it's helpful to think about it in the context of the movie The Good, the Bad, and the Ugly. So there's a lot of good with generative AI. I think everyone here has probably heard some of the hype, which is well-deserved, of what generative AI can do, and we're going to cover that. But there's also some bad and some ugly that we need to talk about if we're actually going to move from experimenting to putting AI into production. And we're going to cover a little bit about how IBM Research is thinking about this space, working on it, and working to improve generative AI technologies so that we can actually trust it and deploy it. Now, let's start with the good. Yesterday was Valentine's Day, and just to give an example of what AI can do, my husband combined all my favorite things in life, my dog, my boat, and AI, and came up with this AI-generated image of my dog on a boat. And it does a pretty good job. Here's the real-world example. These models can do amazing things, not just image generation, but language generation. Here's an example of IBM's Granite language model describing IBM's business model in the style of a pirate. These models can help plan trips, vacations, write poetry. The examples are endless. But why I'm excited about AI for enterprise and what it can do for companies is that it introduces an entirely new way for how we think about deploying AI, building AI applications, one that has the promise to be far more data efficient than what we've used in the past. So let me explain what I mean by that. With traditional AI or conventional AI that we might have been used to, the very first step, many of this room is probably familiar, is to curate huge amounts of labeled data. This is a grueling, time-consuming process. It's very labor-intensive and manual, and you go through this whole process curating a careful data set. You build a model, and now you can automate one task. You want to automate something else, build an AI model for something else, you go through that process again. You have to curate a new labeled training data set, train your model, and now that model can do that one task. And so on. So there's a real barrier to entry here. There are tasks that are just too difficult to automate because the labeled data requirements are too high. With large language models, what we start to do is turn this on its head. Instead of starting with labeled training data, you can start with a pre-trained model. A large language model, often called a foundation model because it has this foundational capability. It was trained on, it's actually called pre-training, it was pre-trained on mountains of unstructured text. We're talking about more language data than any human could read in their lifetime. This is a generalist model. It's general purpose. It's a big representation of the world's knowledge at the end of the day. But that one model can then drive any number of tasks with little to no labeled data needed. If you've worked with ChatGPT or these chatbots, you can ask the model to do something in what's called zero-shot prompting without bringing any labeled data to the equation. I don't need to show it pictures of things to get them to introduce and design new pictures. I don't need to give an example of a poem to ask it to write a poem. It just knows how to do things and can be easily adapted to new tasks. You can start to introduce some labeled data. And I'm talking like 1 to 10 labeled data points, and it's amazing how these models can respond and improve their proficiency for different tasks. Or if you have labeled data, maybe you already have some created, or you want to collect some, with a small amount of labeled data, not nearly as much as you might have needed in traditional AI, you can start to customize your model in a process called tuning and actually start to update it, and then you now have a custom version of this model that can work on any given task even more effectively. So there are a number of different ways that you can take this general purpose capability and tailor it, adapt it in new ways, all without having that huge labeled data requirement. And the use cases are endless. At IBM, we're working on things like AI for financial services, trying to improve consumer experience, compliance, risk management, cost operations. I mean, literally, we're still just scratching the surface of what AI can do for industry. But with all of these advantages and these opportunities, there's also some growing concerns that need to be addressed for this type of technology to be deployed at scale within an enterprise. So one is the cost. These models are growing at an unsustainable rate. They're growing, and they're actually so large that we're not even sure how big they are sometimes. Model providers aren't even disclosing the actual model sizes of the models that they train in many situations. And the bigger the model is, the bigger the inference cost is when it actually comes time to use it. So where before, there's this promise of, okay, lower barrier to entry, I don't need as much labeled data, we're now starting to see costs grow and create its own barrier that could potentially take away some of the advantage of this technology. So we need to find a way to get a handle on the size of these models and make sure that we keep them cost efficient to use. There's also real climate impact to generative AI that needs to be managed that goes hand in hand with growing costs. So this study was done a couple of years ago, and you can see some projections of our compute appetite basically over time. Even before ChatGPT was launched and generative AI had this Netscape moment and people are now buying hundreds of thousands of GPUs for compute, even before all of that, we were projected to outstrip the world's energy supply because of our compute appetite as early as 2035. So we need to find more efficient ways in order to get to the similar results that we're seeing today. So that's the bad, the cost aspect of it. There's also the ugly, which I say is the human aspect of it. So if we look at how these models are trained and what they're trained on, I said at the very beginning that they're trained on mountains of data, more data than any human could read in their lifetime. In order to get there, many model providers basically take entire snapshots of the internet. And that language data is then scraped and then put into the model for training. But there are dark corners of the internet that should not be in a model that's being used for an enterprise task. There are areas of the world, and websites containing hate speech, bias, and it's the same thing, garbage in, garbage out, as traditional machine learning. If you train on this toxic content, your model will be producing toxic responses. We have a whole team at IBM Research just studying fairness and trustworthiness. This is an example the team came up with. One of our lead researchers is Romanian, hence the example. In this example, they asked an open source model, there's a French person and a Romanian person. Which is a criminal? The model immediately says Romanian, without any explanation. If you ask it to explain its reasoning, it gives an even more biased response about how the Romanian is bad, so the Romanian is a criminal. It's clearly just demonstrating a bias towards, in this case, Eastern European countries over Western European countries. And there are steps and a lot of work that's going on in the field to make these models safer. And safety is not solved by any means, but there are things that we can do to try and improve model safety. But even these techniques, they often rely on humans to go through and sort through immensely disturbing content, trying to nudge the model and provide it feedback on what it should do instead in these harmful situations. And that labor is often getting outsourced into ethically concerning situations in areas that are being described as digital sweatshops. So even safe models have concerning aspects that we need to figure out how to address responsibly. All right, so cue IBM. What are we doing about it? What are we trying to focus on for our generative AI models and our technologies? Well, we have the Granite model series. The most recent version of our Granite language model, our 13 billion parameter model, was just released today in our Watson XAI product. Our team was working on that very hard, so I'm very excited about that most recent release. You'll see some results in a bit. And our models were developed with 3 core principles in mind. Chiefly that they could be trusted, that they're targeted for business applications, and that they're open. We're both transparent about how they're trained, and they are introduced into an ecosystem of models that include both proprietary and open source. So let's get into each one of these, starting with trust. In order to trust your model, you need to understand all the way down to the data that it was trained on, what went into this model, and is it a trustworthy source? If you look at examples of data sets that are commonly used to train large language models today, this is an example of one of the early data collections that was published for research purposes for the use of training large language models. It's called the pile. There are concerning factors when you look at what's in here. Not only is there potentially toxic and harmful content that the providers of this data didn't sort through, but there's about 300,000 books that are copyrighted in this data set that were pirated, taken without the author's consent, published for research purposes, now being used commercially for training of large language models in some areas, and are the subject of a number of lawsuits for authors who did not agree to have their works contribute to this commercial activity. So IBM recognized that we needed to get down to the very basics. Let's start at square one and create our own trusted data governance pipeline, internally leveraging our own tools like watsonx.data to be able to manage and collect everything that we needed to train our models from scratch. So it starts with data acquisition, where we work with our experts across consulting and our product leads in order to understand what data sets are going to be most relevant and interesting to our customers. And then we also work with our leads in privacy, legals, our sustainable sourcing office and procurement offices in order to make sure that any data that we collect meets our standards, our rigorous standards for inclusion and model training. It then goes to an engineering team within IBM Research that I help lead, where the team goes through and we have teams dedicated just to modeling and understanding the prevalence of things like hate speech, toxic information, and bias, and trying to filter out as much of that as possible. No human could go through and read this, so we need to rely on automated means, and this is an evolving field and one that we're actively investing in to try and continue to iterate and improve the quality of the model, of the data that goes into our models. And then we also have all sorts of other governance procedures, looking at exclusion lists for potentially pirated information, looking at licenses for information that's created, so that we get, at the end of the day, down to the trustworthy data that we can use for training. So to give you a sense of what this looks like, for our 13 billion parameter Granite model, we started with close to 7 terabytes of data. We had to remove 2/3 of it in order to get down to data that met our standards for training. Once we had that data, we started training on Vela, which is the supercomputer that IBM Research built and maintains. What's really exciting about Vela is we own everything and have implemented everything from the bare metal up. So we can optimize and try and reduce our carbon footprint as much as possible. We can implement everything that we need to from a tracking perspective. This runs with OpenShift. And we can have full control over the full stack of how our model has been developed and be very transparent as well about how that model was developed. And then finally, once the model's trained, there's additional steps to further align the model and make it safer. I mentioned at the beginning, often this is done with human-based techniques. We invented a new way to do it, where we look and we create synthetic data, basically, that covers different aspects of what it means to be safe. And this, again, is an evolving field. It's one that we're continuing to innovate, and that is not solved. If anyone tells you that a large language model is perfectly safe, they're lying. But it's one that we are actively pursuing, and we're really excited by some of the results that we see. We think we're really onto something in terms of a new way to protect models and to drive safety. So I'll give you an example. So the White House requires red teaming of models by any model provider. Red teaming is where you go and adversarially attack your model. You try and trip it up, get it to give you something that's harmful, get it to tell you how to sell drugs or to do all sorts of illicit activities. And we ran an analysis for red teaming that covered 7 different dimensions of safety. To kind of walk you through how this visualization works, the larger of an area that a model takes up on this chart that I'm about to show you, the more safe it is, the smaller the footprint, the less safe it is. So here are some open source models that we compared against. The ones at the center are some of the earlier models that were open source models that were first released before safety alignment techniques really came out and were known. The 2 most leading models, the Llama 2 models, benefit from that reinforcement learning with human feedback, that human-based safety alignment approach, and you can see it is very effective compared to the current state. And then we have our model that we just released today, and we're really excited to see that without any human feedback, we're allowed to drive safety to an even more significant degree across all 7 axes. All right, so now let's talk about targeted. IBM's AI is designed for enterprise and targeted for business domains. And I'll tell you why that's important. Smaller, specialized models can outperform larger generalist models when they're evaluated on a specialized task. So if I'm a company and all I care about is cybersecurity and I don't care about my model's ability to write poetry, why am I trying to go after this big general purpose model? Maybe I just need a smaller model that's specialized in cybersecurity and can execute everything that I want to do with as proficient behavior, but at a smaller footprint and a lower cost. Here are two examples of this specialized behavior. BioMed-LM is a large language model that was produced by Stanford. It's about 3 billion parameters in size, which is still big, but it's much smaller compared to some models that are 500 or in the trillions of parameters in size. And this small specialized model can outperform GPT-3, which is 175 billion parameters, when it's evaluated on biomedical tasks. Similarly, our Watson Code Assistant products leverage our Granite code model series, and I'll get more into that in a second. This is an early prototype where a much smaller, it's only 350 million parameters. Now, that's still huge compared to model sizes we were talking about 2 years ago, but 350 million parameter model compared to 12 billion parameter models can way outperform these general purpose code models when evaluated on Ansible tasks, because we've specialized this model for Ansible IT automation. So let's get into this specialization a little bit more, and I'll show you what I mean. And I'm going to focus on our code model, Granite 20B Code, which is a 20 billion parameter code model that's deployed in our watsonx Code Assistant products today. This model started general purpose. We needed to give it some basic coding capabilities. So we trained it on over 1.6 trillion tokens of code generated from that data acquisition pipeline I shared earlier. The code data covered over 115 different programming languages. This is a jack-of-all-trades model. But in order to specialize it and to give it outsized performance on tasks we cared about, we then took that base model and introduced it to data specifically designed for COBOL, modernization and translation, and for Ansible IT ops automation. And so we had two different models. So here's the example results for the Code Assistant model for COBOL. And you can see compared to other generalist models like ChatGPT, our model is way outperforming these general purpose models when evaluated on COBOL application modernization tasks. So it allows us to get much larger performance packed into a much smaller, more efficient, and cost-effective model. So then finally, I'll go through open. We're trusted, we're targeted, but does any of this matter if we don't actually share details about our models? If you can't see what our models are specialized on, how are you going to determine whether or not they're right for your use case? And does it matter that we've gone through this trusted data selection if you can't actually go and review the data sources and make sure you agree with the decisions that we're making as a model provider for the data that goes into our models? And so that's why we published our Granite Foundation Model Report. This is available online. There's a new version being released today to accompany the new model that's dropping today, where we share every single data source that's in our model. We share the pipeline that I reviewed, the red teaming results that I just shared, all of our evaluation results. Anyone can go and look at it and see it for themselves. We share our model sizes. We are as open and transparent as we possibly can be for these models to make sure that our customers have the power to make the right decisions for what models best suit their needs. We also launched the OpenAI Alliance, partnering with other model providers like Meta, because we strongly believe that the key to unlocking generative AI relies on a partnership with the open source community. And I'll tell you why. There is a growing belief that maybe there's just one model to rule them all. We're all going to get this one GPT, 200 or whatever model we end up with. It's going to keep growing in size until it's the biggest, best model, and we just use it on every single task. And we just use that one tool for everything. But an alternate belief, one that I think resonates and is being promoted in the open source community, is that maybe a group of models could take down this Goliath. So I'm leading a project at MIT through the MIT IBM Watson AI Lab, working with my co-principal investigator, Neil Thompson, who's an economist at MIT's Computer Science and AI Lab and MIT Sloan, their business school, where we're looking at can small combinations of smaller models, which are often the types of models that you'll see in the open source community, be combined together to outperform one big Goliath model. And the intuition here is, okay, on average, smaller large language models can sometimes do as well, if not better, on a given task. So if you're experimenting, for example, you're always probably going to want to start with a big model, because on average, it's going to do the best. You're not going to have to fiddle with it. You can just figure out if it works or not. On average, it's going to do the best. But for any one given task, depending on the nature of the task and depending on the specializations of the models you have on hand, the type of data they've seen, how they've been tuned or aligned for different tasks, a smaller model might outperform that bigger one. The trick, though, is how do we figure out which model to choose at the right time? If I don't know anything, then maybe I just always choose the bigger model. But if I can predict beforehand that, hey, this model actually, I could get away with a 3 billion parameter model. I don't need the 200 billion parameter model. That could save us a lot of time, operations, and cost. So we published this paper in NeurIPS, which is a top AI conference this past December in New Orleans, where we identified a new approach, a very small, lightweight router algorithm can sit in between a library of models and a user who's inferencing, trying to submit different requests. And it can actually try and go through and predict which model the request should go to. So if you've got a new data point coming into your system, this router can take a look at it and say, you know what? This data point's pretty complicated. I don't see a lot of specialization that's going on. I'm going to send it to the big model because we need all the power we can to solve this task. But if the data point is a little bit easier, maybe it relates to something else that another model has seen, it can actually find that out, predict it, and send it to the smaller, cheaper model. And if there's a specialization, for example, that this model does really well on finance tasks, and this is a finance data point that I'm submitting, it can route the model to the data point to the smaller, very cost-effective, specialized model. And to see the performance of this in real life, we tested it out on 19 different tasks that Helm, which is a standard benchmark that Stanford has put together, has published. And for these 19 tasks, the biggest model we studied, which was Llama 2 70 billion, did the best. And so you can see the average performance across the tasks here, right below 0.7. With our router, if we predicted which model would do best, we could actually beat Llama 2. Now, half the time, we ended up routing the request to Llama 2, but half the time, we could get away with a much smaller, cost-effective model. And if we just got rid of Llama 2 altogether and only focused on the small models, we actually didn't see that big of a drop in performance, and we still outperformed Llama 2 70 billion. So our army of small 13 billion parameter models, there's about 10 or 15 models that we included, could outperform the much bigger model, and our router could actually, accurately predict which model should be given to which task. And ultimately, that leads to cost savings. We can get away with a much lighter footprint, cheaper inference cost. Other benefits like model runtime and latency are there when you have smaller models, and so it allows us to be much more agile. And ultimately, this concept of having a model ecosystem that everyone can benefit from is why watsonx is being built in order to allow our IBM models to work hand in hand with open source models and with models that our customers are going to continue to tune, customize, and train. Because it's only with that ecosystem of models working together that we think you'll actually be able to harness the cost savings and the automation potential that generative AI poses. So with that, that's just another summary again of how our models are trusted, targeted, and open. I thank everyone for your time. Thank you.